So there are 6 strong acids in total: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acid. When you have a beaker of these acids, you don't actually have any molecules of the acid because strong acids ionize 100%. So if you have a beaker of hydrochloric acid, you don't actually have a beaker of hydrochloric acid. You have a beaker of hydrogen ions and chloride ions. Or if you're going to do it the formal equation, you add in your water and you have the hydronium ion and chloride ion. Now you'll notice that the arrows that we use for strong acids are single arrows because it's 100% ionization. They're not weak, it's not partial. If you have a weak acid in solution, then you're going to use the double arrows because there will be an equilibrium that's established. So a weak acid, the most common weak acid is acetic acid or ethanoic acid. Usually it's less than 50% ionization. Yeah, so the most common acid used for examples of weak acids is acetic acid, or you know it as ethanoic acid. So again, you can write it the informal way with an H plus and C2H3O2 minus. That's the acetate ion or the ethanoate ion. And you'll notice we use the double bond, the double arrows for weak acids because of this equilibrium. Carboxylic acids. Carboxylic acids are all weak acids. These are our organic acids that we've been studying. And they all have the functional group C double bond O, OH. And there's some number of carbons or hydrogens. Okay, so this is the acidic hydrogen. Sometimes we can write it like this, or we can write it like this. But either way, there's only one acidic hydrogen. So these are monoprodic. One acidic hydrogen. One proton forming. So you can write this the informal way like we did here, or react it with water and make the hydronium ion. Percent ionization tells us how strong the acid is. So percent ionization is basically how much hydrogen ions do we produce. So for strong acids, it's pretty much 100%. Whereas for weak acids, it's less than 50% usually. Sometimes it's as low as 5%. So if I have an acid, let's call it HA. This is my acid. and it ionizes. If it has only 5% ionization, that means only 5% of it makes the hydrogen ions. That means 95% of it remains in the beaker as molecules of acid. So it's going to be a very weak acid. Its pH is going to be pretty close to 7. The K value for this acid, this would be our K expression. This would be very small for a weak acid. Very small for a weak acid, but Ka is very large for a strong acid. We have moderately strong acids, and that means it's usually times 10 to the negative 3 times 10 to the negative 4 in terms of size. But K, if you look up the Ka values, because we call this a Ka because it's acids, if you look up a Ka for a strong acid, it'll say much greater than 1, and there won't be a value. But weak acids you'll be able to find in a Ka table, just like our solubility products. Just like we have strong acids and weak acids, we have strong and weak bases. Strong bases, like strong acids, dissociate 100%. They dissociate into ions rather than ionize into ions because in their formula they are already ions. Hydrogen and chlorine are covalently bonded and they will ionize in water. Bases are ionic, and strong bases are ionic, and they will dissociate into their ions. So that's an example of a strong base. That's actually the most commonly used example. So all oxides and hydroxides of group 1 and 2, except for beryllium and magnesium, are classified as strong bases. So we could find, if we know the concentration of hydroxide, we can find the concentration of H+, and therefore the pH. pH is equal to the negative log of the H+ ion. Hydroxide ion concentration, because we know the concentration of the base. Let's say it's 1 times 10 to the negative 3. Then you can find the H+ concentration using this formula. Find the negative log of that number. and you've got the pH. So if you have a strong acid, so diagrams of a strong acid versus a weak acid. So if we assume that our acid formula for our strong acid is HA and our weak acid is acid HAC. Strong acid would be completely ionized. But our weak acid will be only partially ionized. And that's the difference between a strong and weak acid or base. Now if we look at concentrated versus dilute, if we do concentrated strong versus dilute strong, this is talking about how much acid is in the water, in the beaker. So concentrated means we have a lot of solute. So we will have a lot of ions. Whereas if we have a dilute weak acid, strong acid, a dilute strong acid, it just means we have very few particles in the water in the beaker. So we've got strong, 100% ionization, weak, only some of the acid molecules are ionized. Concentrated, there's lots of ions in the beaker. Dilute, not very much at all. So this is talking about solute, the amount of solute. This is talking about the strength of the acid. We'll do an example. Formic acid or methanoic acid. Formic acid is the acid that ants bite with to immobilize their prey. And that's why sometimes it itches when you get bitten by ants. So methanoic acid is a monoprotic acid with a concentration of 0.10 mole per liter. If the pH is 2.38, what is the percent ionization? And what is the Ka value? So we can get a piece of information from our pH. We can get the hydrogen ion concentration. So we know it's a carboxylic acid, methanoic acid, so it's a weak acid. So it's going to have the equilibrium arrows. So methanoic acid will form the methanoate ion. And that's right there. You take the H off of the OH. So here's our formula for our chemical reaction for our ionization of our acid. So pH, 10 to the negative pH, which is usually the inverse log button, will give us the hydrogen ion concentration. So 10 to the negative 2.38. So this is 4.17 times 10 to the negative 3 moles per liter. So if we do percent ionization first, this is going to be equal to how much acid we make, how many acidic hydrogens we make over the initial amount of acid times 100%. So this is going to be equal to 4.17 times 10 to the negative 3 moles per liter divided by 0.10 moles per liter times 100%. So this methanoic acid only ionizes about 4%, so it's quite a weak acid. Only 4% of its acidic hydrogens pop off of that OH group. For the next part, to figure out the Ka value, we need to use this information, and this information. Okay, so we have to set up an ice table. Initially, we're told our acid is 0.1 mole per liter. Initially, we have no products. Change, they're just X because the coefficient's 1. So this E line is very important to us. This would be our equilibrium values. And this is where we get the hydrogen ion concentration. So we in fact already know what value X is. We know it is 4.16 times 10 to the negative 3 moles per liter because we found it from the pH. So set up your K expression. Ka is going to be equal to your hydrogen ion concentration, your methanoate concentration, all over your acid concentration. So we know our value for X, we can substitute that in. So 4.16 times 10 to the negative 3. This is also X. All over 0.1 minus 4.16 times 10 to the negative 3. So if you plug this into the calculator, you get 1.8 times 10 to the negative 4. So our K value is quite small. So both percent ionization and your K will tell you approximately whether you have a weak or a strong acid. Because they're so small, that means we really do make very little hydrogen ion concentrations. So these are very weak acids. Our second example What is the pH of a solution of 0.75 mole per liter acetic acid? So here's our chemical equation. We've got acetic acid or ethanoate. So our ion, its conjugate base is the acetate or the ethanoate ion. So we're going to have an ice table again. We've got 0.75 moles per liter acetic acid initially. We have no products because it's initial. Goes through a change. And then at equilibrium, we would have this amount present. So now what we need to do, set up our K expression, solve for X. So X times X over 0.75 minus X. And this is acetic acid, so we can find our Ka value by looking it up in the appendix. And it is 1.8 times 10 to the negative 5. So we could use the assumption the 0.75 minus X is approximately 0.75 if 0.75 divided by our K is greater than 1,000. And it's roughly 42,000. So that assumption's correct. So we're going to simplify. So 1.8 times 10 to the negative 5 times 0.75 is equal to x squared. Take the square root of both sides and we solve for x. And x is 3.67 times 10 to the negative 3 moles per liter. We can have two sig figs in our final answer. So 3.7 times 10 to the negative 3 moles per liter. And X happens to be our hydrogen ion concentration. So if we take the negative log of 3.7 times 10 to the negative 3, we will have our pH. So our pH is 2.43. So, for this equation, set up an ice table. Set up your K expression. So now it's a Ka. Solve for x. Find pH using this formula.